North of Puerto Rico, the seafloor falls abruptly into the deepest part of the Atlantic Ocean. Scientists entered this mystery, expecting depth, but found a boundary shaped by oblique plate motion. The trench is not merely an empty chasm. It contains faults, sediments, slopes, and living communities. Each finding answers one question, while exposing limits created by distance, pressure, and incomplete coverage. From the islands, you face an ordinary horizon, above a remarkably complicated submerged margin. The investigation begins with what instruments actually recorded, not what dramatic silhouettes might suggest. Maps found a long depression with steep walls and significant variation along its floor. Earthquake records found active deformation distributed across the trench and surrounding fault systems. Gravity measurements found an unusually strong negative anomaly associated with deep water and crustal structure. Biological sampling found organisms able to function in darkness under intense hydrostatic pressure. These discoveries belong to different scales, from cellular adaptation to moving tectonic plates. Their connection is the evolving landscape that creates hazards and habitats north of the Caribbean. No single expedition discovered the trench's meaning, and no single image captures its complexity. Knowledge accumulated through repeated mapping, seismic monitoring, sampling, and comparison with regional geology. The dominant story is therefore how separate measurements transform depth into a dynamic boundary. The North American plate interacts with the Caribbean plate along this margin. Motion is oblique, combining components of convergence with substantial sideways displacement. Because deformation is partitioned, earthquakes occur on multiple structures rather than one simple trench interface. The North American oceanic lithosphere bends and descends beneath the northeastern Caribbean region. Nearby strike-slip faults accommodate part of the lateral motion across the boundary. This geometry helps explain why earthquake mechanisms vary over relatively short distances. It also complicates estimates of which faults can generate the largest seafloor displacement. Multibeam sonar measures depth and reveals scarps, channels, ridges, and landslide deposits. Seismometers locate earthquakes and infer how faults slipped from the pattern of arriving waves. Satellite geodesy tracks slow ground movement on islands across years. Sediment cores recover physical records of deposition, erosion, and sudden transport. These four methods established the context while leaving much offshore motion indirectly constrained. Mapping confirms a maximum depth exceeding 8 kilometers in the trench system. Pressure there is hundreds of times greater than at the ocean surface. Sunlight never reaches the floor, and temperature remains cold despite the tropical latitude above. Organic particles sink from productive surface waters, losing much of their material during descent. Steep topography funnels some remaining particles into deeper channels and basins. The floor, therefore, receives food unevenly, producing patches rather than a uniform biological desert. Scientists also measured a pronounced gravity low across the trench. This signal reflects mass distribution beneath the survey, including water depth and lithospheric structure. Gravity does not reveal a hollow Earth or an unexplained void beneath the Atlantic. Interpreting it requires models that account for topography, crust, mantle density, and regional compensation. The result is a constrained geophysical picture rather than direct access to deep rock. The first major finding is that the trench's shape records both bending and fault-controlled relief. Outer slope faults cut the descending plate as it flexes toward the boundary. Some scarps appear crisp in sonar, while others are softened by sediment or later movement. Their geometry can indicate extension, but sonar alone rarely establishes recent activity. When you inspect a shaded relief map, lighting choices can exaggerate subtle slopes. Researchers compare overlapping data and seismicity before assigning tectonic significance. The second finding is that seismic hazard comes from a network of potential sources. Historical earthquakes damaged Puerto Rico and neighboring islands, demonstrating regional activity directly. However, uncertain older locations make exact fault assignments difficult for some events. Modern waveform analysis improves source estimates, but the instrumental record spans limited tectonic time. Tsunami evidence likewise demands careful separation of earthquake displacement, landslides, and distant sources. Coastal sand sheets may indicate rapid marine flooding, yet storms can move similar material inland. Microfossils, sediment grading, chemistry, and elevation help test the tsunami interpretation. Secure ages then determine whether deposits correlate across separate coastal sites. The third finding is that submarine landslides have reshaped parts of the margin. Bathymetry reveals headwalls, disrupted slopes, and deposits consistent with downslope failure. Their existence is observed, but the trigger of each ancient slide is often unknown. Earthquake shaking is plausible for some failures, while sediment loading and slope weakness also matter. A mapped landslide is therefore evidence of past movement, not automatic proof of an impending collapse. The fourth finding is life adapted to hadal conditions. Amphipods detect chemical traces from carrion, approach rapidly, feed, and carry consumed carbon away. This documented response helps explain crowded baited recordings without proving natural background abundance. Sea cucumbers move across sediment, ingest surface material, digest organic particles, and deposit reworked trails. Their feeding links microbial production with larger animals while mixing the upper seabed. Microorganisms metabolize buried compounds and alter pore water chemistry within trench sediments. Genetic detection can reveal biological material, but it may drift or persist beyond the organism's presence. Specimens and images remain necessary for confirming anatomy, identity, and actual behavior. Together, these findings replace the idea of an inert abyss with a changing ecosystem. The trench matters because its faults face densely populated Caribbean coastlines. Strong shaking may arrive before detailed source analysis, and local waves can reach shores quickly. You may hear a warning later than natural signs during the closest possible events. Preparedness, therefore, combines seismic monitoring, sea level gauges, evacuation planning, and resilient construction. Forecast models estimate travel times and coastal amplification after an event has begun. They do not predict the exact date of the next earthquake or landslide. Local bathymetry and harbor geometry can strengthen or weaken waves over short distances. This variability makes site-specific inundation maps more useful than one regional wave height. The trench also influences submarine cables that support communication across the Caribbean. Shaking and sediment flows can damage cables, producing disruption far beyond the failure location. Cable breaks sometimes reveal timing of underwater flows, although they are not purpose-built scientific sensors. Repair operations must navigate steep terrain, deep water, and continuing aftershocks. Understanding sediment pathways, therefore, supports both hazard science and infrastructure planning. If you descended toward the floor, darkness would arrive thousands of meters before the bottom. Vehicle lights would reveal suspended particles, soft sediment, and occasional animals within a narrow field. Pressure would constrain housings and seals, while acoustic communication would replace ordinary radio. That direct view would remain local, requiring maps and regional data to establish context. The trench's remoteness is thus technological, not biological or geological isolation. Its sediments receive material from above, and its faults connect with a broader plate boundary. Future work must turn scattered findings into sustained measurements across the margin. Seafloor geodesy could measure motion closer to submerged faults than island stations permit. Denser ocean bottom seismometers could improve earthquake depths and reveal small offshore fault clusters. Repeat sonar surveys could identify fresh scarps, slides, and channel changes after major shaking. Long core sequences could extend records of rapid deposition beyond written history. Pressure-retaining samplers could test how hadal organisms function without damaging decompression. Unbaited camera transects could estimate natural behavior alongside attraction-biased lander observations. Chemical profiles across sediments could connect organic supply with microbial activity and burial. Researchers could then test whether biological hotspots follow topography, currents, or recent disturbance. No method alone can determine which mapped fault will rupture next. The strongest conclusions will come from agreement among independent observations with known uncertainties. Those gaps should guide surveys rather than invite invented monsters or hidden mechanisms. The opening Atlantic chasm has yielded structure, motion, life, and evidence of repeated disruption. Its gravity low is explained physically. Its hazards are real, and its timing remains uncertain. What scientists found in the Puerto Rico Trench is a dynamic boundary still only partly observed.